So step functions goes actually on the last bit of the notes that we took on Monday, where we were doing one-sided limits analytically. And we looked at one-sided limits with piecewise functions, related to square root functions, related to absolute value functions. And then the last piece was step functions, and this pertains to, I believe, 2 of your homework problems, if I remember correctly. Quick review of what a step function is. This is what it looks like for the record, this kind of 2-bracketed X. In terms of graphically, it helps to know the other name for a step function, which is the greatest integer function. Because the question you're asking as you lay out your graph is, what is the greatest integer? So integer, remember, whole number. So greatest integer equal to or less than the number that I'm considering, the number that I'm plugging into this function. And so I typically like to start with my integers because it's a pretty straightforward question. So if I was to start here at x equals 0, the greatest integer equal to or less than 0 is 0, because it's equal to. And the greatest integer equal to or less than 1 is 1, because it's equal to. The greatest integer equal to or less than 2 is 2. Same with 3 is 3, -1 would be -1, -2 would be -2, -3, -3 here. And so that gives you kind of the beginning structure for your graph. Now it's called a step function, if you remember from last year, because they create little steps. And figuring out whether the step goes to the right or to the left of your point, you want to consider that question. What is the greatest integer equal to or less than the considered x? So I usually start on the positive side because it's a little easier for most people to think about. And so if we were to consider, for example, here, x equals 0.5. Well, the greatest integer equal to or less than 0.5, it was not going to be equal to. 0.5 is not an integer. It's not a whole number. So we're concerned with that less than. Well, less than 0.5, the greatest integer would be 0. And so at 0.5, I'm 0. Maybe you consider 0.75, the greatest integer equal to, so not equal to, it's 0.75, or less than 0.75 is 0. And 0.25 would also be 0. And so what you end up with is all these 0 points here, creating this line, this step, over to 1, at which point you've got a little hole at 1, 0, because at x equals 1, my function has popped up to y equals 1. And then if you are comfortable seeing the pattern at this point, you can go ahead and lay it out if you need to. Maybe ask that question a couple more times to yourself. So maybe at x equals 1.5, so 1.5, what is the greatest integer equal to, so not equal to, 1.5 is not an integer, or less than 1.5. Well, less than 1.5 would be 1. So at x equals 1.5, my y would be 1. And x equals 0.8. X equals 1.8 would have the same answer as 1.5, because 1.8 equal to, not equal to, 1.8 is not a whole number, or less than, so less than 1.8 is 1. And so same thing, you have this series of points that sits here at 1 over to x equals 2, at which point we pop up to 2. And maybe at this point you see the pattern, so you could continue that, or again, ask yourself about 2.5 and 2.9 and that type of thing, but you end up with this step function. And you could also continue that down the road, so this would go over, over, over. Do make sure you're cautious with the negative side. That's why, like I said, I usually start with the positive side, because people have a little bit more success with the positive side. With the negative side, I sometimes start to see students do this. Negative 1.5, and they know that that's not an integer, so they skip the equal to. And so they're thinking less than negative 1.5, and I start to see students saying negative 1 as less than negative 1.5. But negative 1 isn't less than negative 1.5, is it? Not in negative lands. Less than negative 1.5 would actually be negative 2, which is why if you notice when I kept this pattern going at negative x equals negative 1.5, I was plotting it at negative 2. Okay, so just watch the negative side of things. Okay, so we've graphed it. That's going to help us to answer our questions here. So I could potentially ask you for the limit as x approaches 3 from the right of 2 times the step function of x. Okay, well, the reason we need a one-sided limit is because if I look at x equals 3 here, 1, 2, 3, and I notice at x equals 3, I've actually got 2 things approaching x equals 3. One's approaching from the left, one's approaching from the right, and they're 2 different numbers. From the left, I'm at 2. From the right, I'm at 3. And so depending on what direction they give me, or what, I should say, starting place they give me, it's going to change what number I'm using in solving this limit and evaluating this limit. And so if I'm looking from the right, that's this function here, so that's what's approaching from the right, and that is at 3. And so this is going to be 2 times 3, which is 6. I also could potentially ask you for example 2, the limit as x approaches negative 2 from the left of, and we'll do 3 step function of x minus 1. Well, negative 2 from the left, here's negative 2. From the left would be this function here. I'm sorry, this function here is from the left, which that is at negative 3. So this is going to be 3 times negative 3 minus 1, which is negative 10. Okay, example 3. We're going to do 2 more here, but I'm going to challenge you, if you're watching this video, to write down the problem when I put it up, but then pause the video, try it on your own, and then restart the video to check your answer. That way you're seeing, you know, am I actually understanding this or not? Right? So let's do the limit as x approaches 4 from the right of 5 times the step function of x. Okay, give this one a shot. Okay, 4 from the right. Now I didn't actually graph x equals 4, so if I wanted to see it, I could go ahead and extend this graph and maybe graph x equals 4. X equals 4, remember, would be up here. And there would be my extra step. And if I'm looking at 4 here, and I'm approaching from the right, that y, that limit, is 4. So this would be 5 times 4, which is 20. Okay. One more for you to try. Limit as x approaches, let's do 0 from the left of, and we'll do 1/2 times the step function of x plus 3. Give this one a shot. Okay, so approaching 0 from the left is right here. So here's x equals 0, so we're talking this function. That's approaching 0 from the left. And that's at negative 1. So this is 1/2 times negative 1 plus 3, which is negative 1/2 plus 3, which is 5 halves, or 2.5 if you prefer the decimal. Okay, and that's step functions.